Okay, so welcome back to another video. So here we have a definite integral from 0 to pi over 4 of the square root of tangent x subtract tangent square of x. So I like to call this integral an all-in-one. I know that phrase kind of sounds a little vague, but actually when we're actually going through the entire procedures evaluating the value for this integral, there's a lot of formulas that come into play here. Not only that, you'll see that there's going to be a sum, there's also functions, beta, gamma. There's actually going to be involving factorials and the double factorial as well, which that's never been covered in any of my videos before. So that's also a first. And of course, actually there's also a little bit of complex analysis a little involved with that as well, but that actually comes more towards the end of the video that we get into that sort of manipulation. So that's really all I really want to say for in terms of discussions and what to look forward to ahead of time. But yeah, everything's all in one. You're going to see a bunch of formulas, a lot of techniques, a lot of manipulations. Personally, I think this is probably going to be I wouldn't really say the longest video, but in all my past videos, I've dealt with integrals. I know like the past videos have been like way longer, more along the lines that I don't usually like cut a lot of footages since I just saved that work. But in terms of, workload, this is probably going to be a bigger one than the rest of the previous integral videos that I cover. So anyway, with that, let's just get started and have some fun. So first, we start with a u substitution. We suppose that, and I'll call this entire integral capital I, so I'll save this later. So we'll start with a u substitution. I'll call this t is equal to tangent x. So what we do is, of course, now we want this to solve for, put this back for x. So, but now that means that we can actually put this for the new bounds. So that means I have that x is equal to inverse tangent of t. And another thing to add is that also that we want a dx differential as well. Otherwise, if we differentiate in terms of dt, that makes things a little bit difficult to work around with. But with dx, so now we can differentiate both sides. So dx is then just equal to 1 divided by 1 plus t squared and then dt. And then now with this, we have our new bounds. So I and then is equal to, so plugging this back for 0 pi over 4 for x, we're going to get that the new bounds for in terms of t is that we have, this is from 0 to 1 of the square root of t minus t squared, and then all this being divided by 1 plus t squared dt. Now, another thing we can do, we can actually do a little bit of rewriting in terms of a sum. So we know that specifically that if we're taking a look at 1 divided by 1 plus t squared, and it's nice that because our integral is in between 0 to 1 over t, 1 to 0 to 1 in the variable t, so we can actually apply the geometric series and say that specifically 1 divided by 1 plus t squared is the same thing as written as the infinite sum from n is equal to 0 of negative 1 to the power n, and then multiplied by t to the power 2n, for of course t, the absolute value of t is strictly less than 1. So with this, we can actually plug back that substitution, and so we have now the integral from 0 to 1 of the square root of t minus t squared, and then multiplied by the infinite sum of from n is equal to 0 of negative 1 to the power n, then t to the power 2n dt. Then I can actually just exchange the sum and the integral outside and put the negative 1 to the power n outside as that as well. So we have the infinite sum from n is equal to 0 of negative 1 to the power n, then multiply with this integral of t to the power 2n plus 1/2. And this is just a little bit of rewriting with the square root of t minus t squared and then multiplying it with the same base. So afterwards, now we'll have that this then afterwards multiplied by 1 minus t quantity to the power 1/2 dt. So with this, I'm sure that now with this integral we have to calculate, but this is actually comes in a very similar formulation. And if you can guess by now, or if not, that's okay. This is actually the form of a beta function, and the beta function, specifically the integral representation of that. And actually we will also be using in terms of gamma as well. So, it's always important to, it's always important, but it's also nice to have that as well when you comes to solving these kinds of problems. So we know that beta of some two variables m of n is going to equal to the integral from 0 to 1 of t to the power m subtract 1 and then multiply by 1 subtract t quantity n subtract 1 then dt. And I'll put this as a slash that we'll also be using gamma representations of that as well, because that'll also be important later when we evaluate this integral. So this is gamma of m times gamma of n, and then divided by gamma of m plus n, the sum of those two inputs. And so with that, now let's actually rewrite this entire integral. Well, let's first evaluate the integral that we want. So I'm going to just pay our attention towards the this definite integral over here. So what that comes down to is that this is actually going to equal the following after I write this down. In terms of just the beta of capital B itself, this is actually our two inputs are going to be written as follows. So we have 2n plus 3 over 2, and then the second input's going to be 3 over 2. So with that, now let's actually now write this in terms of a gamma function representation. So that in terms of gamma, so that means we have gamma of 2n plus 3 over 2 multiplied by gamma of 3 over 2, and if we just add the sums together, so we have gamma of just 2n, and then add this with 3. And so with this, now we had to actually evaluate this gamma function over here. So let's actually start with that. So let's first start with we're going to actually use a recurrence relation. That first we have that gamma of some u plus 1 is going to equal to, of course, u times gamma of u. And it's also well known that eventually, as we solve this, we're going to have that gamma of 1/2 is equal to square root of pi. We know that calculation. So then the next recurrence relation we're going to use, and this actually works for positive integers, that says that gamma of n plus 1/2 is going to equal to so 2n minus 1, and this is the double factorial, multiplied by the square root of pi, and then divided by 2 to the power n. We put 4, n is a positive integer, but plus. If this recurrence relation looks new to you, you can actually all it is that you take this recurrence relation and you just repeat this iteration, so on and so forth, in order to obtain this closed form. But of course, if you want to show that, then inductions and proof by induction is of course your friend for this. But I'm not going to go into detail with that. So now let's actually calculate these two gamma values, specifically gamma of 2n plus 3 over 2, 2n plus 3. 3 over 2 is basically, again, I said that we'll be using that gamma of 1/2. We know that that's equal to the square root of pi, and then if we just plug the 1/2 back into here, that actually gives 3 over 2. 1/2 multiplied by gamma of 1/2, of course, is just square root of pi divided by 2. So at least that's one value out of the way that we needed to solve. So let's actually start off first with calculating gamma of 2n plus 3 over 2. So of course that recurrence relation that I just put down for positive integers and just like so is going to be very useful in this situation. Now let's see. So we'll start with gamma of 2n plus 3 over 2. Okay. So we know that if we just rewrite this a little bit to fit this recurrence relation, we can actually use the input of 2n plus 1 and sub that substitution for just some standard n. So we'll get that this is 4n plus 1 double factorial times the square root of pi, and then this is being divided by 2 to the power 2n plus 1. So this is actually going to be a little bit interesting. So we're doing a little bit of simplification and rewriting. If you don't know how double factorial works, of course, like a standard factorial, it decreases by each number, but in this situation, double factorial deals with parity. So in other words, like odds and even numbers. So for example, if you were to have something like 5 double factorial, so basically it's 5 times 3 times 1. So as you heard from those numbers, those are odd integers. Or 10 factorial, 10 times 8 times 6 times 4 times 2. Those are even integers. So how can we do a little bit of rewriting over here? So first, as you notice that, and I'll erase this later just to fill in more room, but we're just gonna give a little bit of a demonstration how this works. So of course, if we start off with 4n plus 1 double factorial, so we're taking a look at this, for example. So if we were to just expand this out, this is clearly written as 4n plus 1, then 4n subtract 1. So remember, just dealing with the odd integers, it's like a decrease of each pairs of 2s. Then 4n minus 3, keep on going so forth. 4n minus 5, 4 times 4n minus 7, you get so. So what's nice is that if we actually look at 4n plus 2 factorial, so this is actually dealing with every single integers that we see. So this is 4n plus 2, then 4n plus 1, then 4n minus 1, so on and so forth. Now, okay, so where are we going with this? Now suppose that if we take a look at 4n, add this with 2 double factorial, factorial. So of course we're dealing with even integers. So 4n plus 2, then 4n, then 4n subtract 2, 4n minus 4, so on and so forth, minus 6, minus 8. Now, if I actually take the division of these two, so 4n plus 2 factorial, divide this with 4n plus 2 double factorial, then we see that if we expand this out, then you can see that this is actually canceling out the even integers and left ones with the odd at the end. So 4n plus 1, 4n minus 1. Then that actually exactly matches with the identity of 4n plus 1 double factorial. And so with this, we can actually use this as a substitution of that identity in order to make things a little bit easier for that entire evaluation of, simplifying the following over here. So with this, let's actually get onto that, and I'll just erase this piece. Afterwards, with that, as I just discussed, so that means we have that 4n plus, so this, in other words, is written as 4n plus 2 factorial, then times the square root of pi, and then we divide this by 2 to the power 2n plus 1, then multiply by 4n plus 2, and then double factorial. We can actually do a little bit of more rewriting, and this is actually going to make things, this is going to help things a little better, and you'll see where I'm coming from with this. So another thing to note is that as you see that, we're actually going to rewrite the 4n plus 2 double factorial a little bit differently. So here's something to look at, and I think this is actually pretty cool to see here. So as I know I erased it, but I'll just write this out again. So as we see, we know that 4n plus 2 is written as 4n plus 2 times 4n times 4n minus 2, so on and so forth. Notice that everything can be factored out as 2. So in other words, I can say that this is like 2 times 2n plus 1, then times 2 times 2n multiplied by 2 times 2n minus 1, so on and so forth. Everything can be factored out with 2. So in other words, you'll notice that I can factor out all the 2's, but they actually appear 2n plus 1 times. So in other words, this is 2 to the power 2n plus 1. However, you factor this out where it ends on the left-hand side by that expansion, then that's how many times the 2's are placed into this expansion. But at least it decreases by 1, so 2n plus 1, then 2n minus 1, 2n minus 2. So we can actually convert this as just a single exclamation point, just a normal factorial of 2n plus 1 factorial, which is nice since we have factorial here, factorial there. So we don't need to, that actually gives us less of a headache to deal with the double factorial of that simplification. So afterwards, so as I just described, of course, that's the identity we'll be using, so that means that actually fixes up the denominator so much better. And so when I said that this is 2 times 2n plus 1, of course we got to multiply that by that base, so that just the exponent just doubles over there. So 4n plus 2, then multiply, so double factorial, then times the square root of pi, then divided by 2 to the power 4n plus 2, multiplied by 2n plus 1, then factorial. And what's interesting is that this actually also works for n is equal to 0 too. So that means therefore this left-hand side is equal to this right-hand side over here, also for n are positive integers, and I just create the set with the union of the singleton 0 as well. So that's nice. So that actually gives us a little bit more lineage to work with. So that actually completes the gamma of 2n plus 3 over 2 simplification. Okay, so let's move on to the 2n plus 3, which actually, to be fair, this is the only easy part this is the only hard part that we have to, rewrite in terms of our understanding to make things a little bit better for us. So the next part actually, as I mentioned, 2n plus 3 is that we just have to use, the relation with the gamma function as well of the extension of the factorials. So we know that gamma of n, let me actually write on the top right corner, at least we got some room there. So we know that gamma of n is actually just equal to n minus 1 factorial. Okay. And so with this, now if I just plug in gamma of 2n plus 3, then I've actually just plugged that back in to say that this is just 2n plus 2 factorial. Okay, and then we also say that gamma of 3 over 2, of course that's the same thing as 1/2 times gamma of 1/2. We know that gamma 1/2 square root of pi, that's just equal to the square root of pi divided by 2. Okay, so what's nice, that's great. So now after plugging all this back in, so let me write this gamma out again one more time. So gamma of 2n plus 3 over 2, then multiplied by gamma of 3 over 2 divided by gamma of 3, or excuse me, 2n plus 3. Now we just plug all this back in, so we'll actually have the following identity over here. So we'll have 4n plus 2, then times the factorial, not times. 4n plus 2 factorial, so divided by 2 to the power 4n plus 2 times 2n plus 1 factorial. Then we multiply this by the square root of pi divided by 2. Then we just divide this by 2n plus 2, then factorial. This is going to be a little bit interesting to simplify. You guys can see this. Well, so that means that, with the division, that means I could just put this underneath over here. What I can do is I'll multiply this 2 back here, then that means this will increase by from 2 to 3. And then what's nice is that 2n plus 2 factorial, of course, is the same thing as writing as 2n plus 2 multiplied by 2n plus 1 factorial. And another way you could say that is that if you remember by the binomial coefficient that says that n factorial, it's n choose k is equal to n factorial divided by k factorial times n minus k factorial. And if you actually plug in with the factorials carefully, and that you were actually going to get this following simplification. I know this is actually very long and takes a while to just get used to all of that. But afterwards, the square root of pi's cancel out. So first I have a pi divided by 16. And then we have 2 to the power 3. And then, of course, I said that we have a 2n plus 2 on that side, so I'll factor out that 2. So that's how we get that 16. So then afterwards, I'll also just leave that as a n times 1. So I'll have 1, then divided by 2 to the power 4n multiplied by n plus 1. And then that binomial coefficient helps since we have a 4 plus 2 factorial. And then with the whole 2n plus 1 factorials, if you actually do the math over there, we get a binomial coefficient of 4n plus 2, and then choose 2n plus 1. Okay, and so with this, now let's actually write this in the simpler terms, that meaning that now that we figure out what our integral representation that we just calculated over here, now we can just plug that back into our alternating sum. So let's see. Therefore, the infinite sum of n is equals 0 of -1 to the power n of the integral from 0 to 1 of t to the power 2n plus 1/2, then multiplied by 1 minus t, then to the power 1/2 dt is going to equal this following over here. So we'll have pi over 16 as a constant, then we have multiplied by this infinite sum, and this equals 0 of, what was it? The alternating -1 to the power n, and then divided by 2 to the power 4n, multiplied by n plus 1, and then we have multiplied by the binomial coefficient 4n plus 2, choose 2n plus 1. Okay, so far that actually is what we're at the moment, and I think I'm just gonna say personally that I don't think we're halfway through, so we still have a while to go, so bear with me on this if this is too long. So anyway, with this, let's actually, I'm gonna erase this half, and then we're actually gonna continue forward with the work. Okay, so far we've shown that the alternating sum, -1 to the power n, of this integral is indeed equal to the simplification that we use with the whole double, factorial and factorial simplification, just like so, including with the association of the binomial coefficient. So where can we go from here? As mentioned, that we'll be actually using a little bit of complex analysis, but for right now, well, yes, we will be using that, but we'll actually be using the imaginary numbers into our usage in order to make the simplification a little bit, worthwhile to work around with, easier in another sense. So with that, what I can do from here is I'm gonna not only multiply an I to both the numerator and denominator, I'm gonna move the factor of 4 from the denominator, put that back in. So yes, this says 2 to the power 4, but that's also the same thing as writing it as 4 to the power 2. So we're putting that as in terms of base 4. But also another way to write this with that -1 is the same thing as, I square. So and then we just distribute the n into that and the I as well, since I'll also be multiplying and dividing an I. Everything for future steps will actually comes out nice. So after performing all of that, so we'll put this as, now this is going to be pi divided by 4i. Then we multiply, well, of course, with infinite sum, n is equals 0. So this is what we're going to have. We will have I to the power 2n plus 1. And then we divide this by 4 to the 2n plus 1. As I said, I factor out the 4, put this back here, change the 2 to the 4 to 4 squared, and distribute the n as well. And of course, that's still n plus 1. and then multiply with the binomial coefficient for n plus 2, and then choose 2n plus 1. I think this is the n plus 1 is kind of like getting into our way of writing things a little further. What we do know is that we know that 1 divided by n plus 1 can be rewritten in the form of this following integral. 0 to 1 of x to the power n dx. So that's actually the next step we'll do. We're actually going to make this back into converting it into an integral. And then we have some other steps we'll follow. So let me actually first write what we need to write. So we have pi over 4, pi divided by 4i. And then we have the integral from 0 to 1 of, the infinite sum equals 0 of I to the 2n plus 1, then multiply by x to the power n, and then same thing, 4 to the power 2n plus 1, multiply by, actually never mind, forget the n plus 1, because again, there is that definite integral that we went backwards with, so now the denominator is only just left with 4 to the power 2n plus 1, and then we multiply with the binomial coefficient written as, the same as always. Just like that. Here's going to be a little bit of more manipulation that we're going to do. So this is the next step here. There's actually going to involve the square root of x in this simplification. So that we're actually going to multiply and divide a square root of x from this integral slash sum hybrid. So what this comes down to now is that we have pi divided by 4i. Then the integral from 0 to 1 of, now this can be put outside of our sum. So I have 1 divided by the square root of x, then the infinite sum from n is equal 0, I to the 2n plus 1. Then we multiply, so this is going to be, the x can be written as the square root of x squared, put that back as well. Then multiply the square root of x as we have this multiply and divide over here. So the square root of x, then quantity 2n plus 1, then divided by, of course, 4 to the power 2n plus 1. Then with the, I also forgot to write dx over there, so I'll put that back in just a sec. So 2n plus 1 and then dx. There's our simplification so far. This integral over here, we have square root of x. Then, of course, we put back the square root of x. As I said, that square root of x to the power n is the same thing as square root of x quantity to the power 2n, then plus 1 because of, the multiply and divide from over here. That prefers that same equality just like that. Okay, so now here's where things get a little complicated. So how do we evaluate this whole thing? Well, let's actually first pay into our attention and evaluate this infinite sum. So that, let's actually just jump into that. So the infinite sum we want to evaluate now, and I'm just gonna call this, we'll say that this is, S, for example, for some letter, some arbitrary letter. So we want to calculate, so I'm going to write that same thing, that same sum again. So we have this, so we have that, our sum that we want to calculate. So this probably looks a little bit difficult to manage around. Here's a little something interesting. So if you pay attention for the binomial coefficient, if we actually just use that factorial definition, of n factorial divided by k factorial times n minus k factorial, if we use this for our n and k values, then we see that you'll notice that this is actually 2n plus 1 is the double for 4n plus 2. Okay, that actually follows a nice identity that says that the 2n choose n is written as 2n factorial divided by n factorial quantity and then square. So if this is new to you, and for anybody that's seen this before, you might know that this is actually part of the central binomial coefficient. So if you notice that if you plug the values in carefully and it's a double, then it actually matches the exact same thing. And so for one, we can actually replace this binomial coefficient with this central binomial coefficient over here as a substitute. And then not only from there, we're actually going to do a little bit of creative turn and actually split the sum into 2 as a difference, because there's also some factors we want to consider for, specifically the imaginary unit I, as there's, because for one, there's an exponent 2n plus 1, so it can range from either 1 or positive 1 or negative 1. We consider the positive and the negative, so negative, positive I. So that's actually going to make things a little bit helpful. So difference of sums, and then afterwards we're actually going to compute those sums that afterwards they'll make, well, after computing those sums, it actually make things a little easier from there. So after performing all this identity out and the substitution, as I just mentioned, this is actually what we're going to get with the following. So this actually comes down to 1/2, then multiplied by the infinite sum, of course, from n is equal to 0 of I to the power n multiplied by the square root of x quantity to the power n divided by 4n, then with the binomial the central binomial coefficient of 2n, choose n, then of course subtract that with 1/2 multiplied by the binomial, or the infinite sum, n is equal to 0, of -1 to the power n multiplied by I to the power n multiplied by the square root of x to the power n divided by 4 to the power n. And then that's then multiplied with binomial 2n, choose n. That's great. So now this actually comes as a nice identity we'll be using, which is, of course, as I said, the central binomial coefficient. But this is also nice to say that there actually a following form exists for the generating function of the central binomial coefficient, which comes down to the following. So this says that we have the infinite sum from n is equal to 0 of 2n, choose n, that's actually the coefficient itself, multiplied by some generating function. So from some power series of x to the power n, this actually comes down to a nice close form of 1 divided by the square root of 1 subtract 4x. So with this, we can see that there are some values that we have to carefully choose, but that's actually not that difficult. So you'll see that the value that we choose for the x, we substitute that for the following. So that's a -I, then times the square root of x, then divided by 4. It actually comes out of here. You substitute x for whatever the value is written as followed. You plug that in, then you'll see that actually the 4 cancels. And so from here, we're going to get that the following, now capital S is going to be rewritten as 1/2 multiplied by 1 divided by the square root of 1 subtract I times the square root of x, then subtract 1/2 multiplied by 1 divided by the square root of 1 plus I times the square root of x. So that's awesome. And so putting this back in for the s back into our integral over here. So now we have, now we actually have some difference of integrals by after applying linearity, which is nice. So this actually comes down to now applying that steps after I just mentioned that. So now we're gonna have that this is pi divided by 4i, and then of course I'll distribute the pi over 4i into that difference of integrals. So we have the integral from 0 to 1 of first just 1/2, then times 1 divided by square root of 1 minus I times square root of x dx. Then we subtract, of course, pi divided by 4i, then the integral from 0 to 1 of same thing, but now instead of the minus, this is actually just going to be the plus. So 1 plus I times the square root of x, and then dx. So we just need to calculate each thing one at a time. Oh, I forgot to mention that I totally disregard the square root of x to that. So let me actually fix that up. That actually goes for both of those integrals. So let me just fix that up just a second. And so from here, after all that, now we can actually apply the u substitution. So we let u equals the square root of x, then du is equal to 1 divided by 2 times the square root of x. This is great, so that actually gets rid of that. And now we're gonna have the new simplified integral in terms of u. So we have pi divided by 4 times I, and the bounds stay the same, thankfully. So 0 to 1 of 1 divided by the square root of 1 minus I times u, then du, then it actually applies to the same thing over here. So pi divided by 4i times the integral from 0 to 1 of 1 divided by the square root of 1 plus I times u, then du. Okay, so again, you just apply u substitution again a second time for here, and then after performing all this out, you just let you just let a new variable, we'll call this v, be 1 minus I over u, I times u, and then same thing over here, 1 plus I u. Then performing all this out, then we get something simplified even further. So this is going to be pi divided by 2. Then we multiply. This is now the new this is the antiderivatives written as follows. This is square root of 1 subtract I times x, or rather terms of u. I'm sorry about that, since this is now in the u world. I times u. Then this is from 0 to 1, subtract, well, now this is with the negative, so now that actually fixes that up to change to a positive. So plus pi divided by 2 of, now this is going to be the square root of 1 plus I times u, then from 0 to 1. And so after just plugging all this value in, so we're actually now going to get that afterwards. This is plugging those values, so it's pi times 2, multiplied by the square root of 1 minus I, and then add this with pi divided by 2 of the square root of 1 plus I, then, and plug in the 0, so we get pi over 2 and then pi over 2, and now afterwards that's going to become subtract pi. So we're actually just about almost done from here. So there are more complex analysis that's actually going to be involved here. But actually, these are actually simple, numbers specifically that we're going to use a little bit of the polar form and Euler's formula. So the next thing we want to notice is that now let's take into our focus into specifically what's underneath those two radicals, 1 minus I and then I plus 1. Okay, so let's see. I plus or 1 plus I, we know that we can represent that if we think of this in the complex coordinate system. If we go 1 to the x to the real part and then I up 1, that's the imaginary part, we see that that's actually in the polar form that actually forms pi over 4 in radians. So in other words, and also if you calculate the distance, so the square root of 1 square plus 1 square, since 1 multiplied with the I is associated with that. So we get that this is actually the square root of 2 and then multiplied by e to the power I pi over 4. Okay, then same thing for over here. So we have 1 minus I. If you think of the same thing, except it's actually tending towards downward. So it's negative pi over 4 in that the argument is formed from there. So, and then same radius as well. So it's be the square root of 2 times e to the power I, then times negative pi over 4. Okay. Then now what we can do now is just take the square root of both sides. So square root of 1 plus I is now going to be, now that'll change to the 4th root of 2, then multiplied by e to the power I, then pi divided by 8. Same thing over here, take the square root of that, 1 minus I is equal to the 4th root of e, and then multiply of e to the power I, then negative pi divided by 8. So we actually just put the pieces together back into here. For one, I can also factor out a pi over 2 specifically for these two first terms we're looking at. So that actually comes down nicely to say that this is going to be pi, draw an arrow over here. We're going to have that this is pi over 2 factor out from here. So now actually plugging all this back in. So now we're going to have that this is the 4th root of 2 and then e I pi over 8, then add this with the 4th root of 2 of e to the power I, then negative pi over 8, then subtract pi. Then I'm actually going to factor out some stuff. For one, I'm actually going to distribute the 2 into our parentheses, then factor out the 4th root of 2. So now this will be pi times the 4th root of 2. Now multiply with e to the power I, pi divided by 8. Add this with e to the power I, then negative pi divided by 8, all this being divided by 2, subtract pi. We notice that by the definition from complex exponential, this is actually the same thing as cosine of pi over 8. So 2, 4, then cosine of pi over 8. Then that actually comes down, cosine of pi over 8 comes down to the value of the square root of 2 plus the square root of 2 divided by 2. And you can actually use the identity that we know that cosine of pi over 4 is square root of 2 over 2. Use the identity that cosine of theta divided by 2 is equal to plus / minus square root of 1 plus cosine theta divided by 2. Plug that back in. We're only considering the positive since that's where positive pi over 8 falls on the first coordinate. Plug that back in and that's how you get that value. So after plugging all this out, we're going to get that the final answer, and then simplifying everything out coming together is now going to equal to just pi times the square root of 1. Add this with the square root of 2 divided by 2, and then subtract pi. And so just like that, that is the final answer of this entire definite integral with a whole I'm losing my words. That's our final answer of our definite integral over here. That's actually, we suffered through a lot of workload. I know I had to erase this the first time to make even more room, but this is the final answer it comes down to. As you can see, you can also plug this on Wolfram Alpha. It comes down to 0.310025. That is actually, this is the number that it approximates to. So there we have it. So yeah, that's pretty cool if you ask me.